screen.
Yes, sir.
Can you check with Devashish and Malay who could not? Devashish, can you read what I have written?
Yes, sir.
Okay, very nice. So the only thing is now, since you cannot log into this, enter this one, probably you cannot write. But if you want to say something, you can shout. Then somebody else will write. Okay, so those of you who could not join this board, so you can at least see the proceedings and then you can speak. So this is our system. Now, maybe I can invite one of you. So let's say, Susinder, are you there? Susinder?
Yes, sir.
Okay. So the question, Susinder, is that we have n non-interacting particles. So I want to find out the partition function. Okay, the question is find the partition function Z. What simplification do you think this non-interacting particles will help you to find this Z? Is the question clear?
Yeah, yes, sir.
Okay, this is not an examination, so all of you should feel free and just think
So
that it is a
probably we
classroom.
can add those two energy levels since they are not interacting.
We can add those two energy levels
Of the n non-interacting particles
to get what?
to get the partition function.
How do we add it? See, I have like first particle here, second particle here, third particle here, let's say nth particle, and each of them can be in one of the two levels, right? Each of them can be in one of the two levels. So this is the kind of system that we have in mind. But I am giving this information that they are non-interacting. So if they are non-interacting, then what is it that we can do? Okay, so let us ask another Sweta. Sweta, are you there? Listening? There is probably some delay, but this delay is more than what is allowed by special theory of relativity. Okay, Anandu, do you have any suggestion? I think your audio is not working, but can you write? Sweta has joined. Okay, this is probably new to all of us. So, Shruti, are you there?
Yes, sir. Yes, sir.
Shruti, do you have some suggestion? How do we simplify our finding of Z if n particles are non-interacting?
I'm sorry, sir. I have no idea.
Okay. So Anand Kumar Tiwari.
Yes, sir. Sir, I cannot write, but I can tell whatever I have to do.
Yeah. 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 Go
So,
ahead.
first of all, I have to write the Hamiltonian, and Hamiltonian. This here, since it is non-interacting, so potential will be zero. So Hamiltonian will contain only the kinetic energy term, that is p square by 2m, and then we have to write here, since it is two energy levels.
Hmm.
So we have non-interacting particle, each of which can be, so z is equal to, first of all, z is equal to summation of
Hmm.
exponential की power minus beta e. So beta e I. So here I will be, since each particle will contains two energy levels, that is can take two energy levels, that is 0 and epsilon. So here summation will be over the from 0 and epsilon. So my partition function will be z is equal to, for one particle. First of all, I am writing for one particle. Then I will just take z1 की power n to n particle. So z is equal to exponential की power minus beta multiplied by 0 plus exponential power minus beta multiplied by epsilon. So exponential power 0 is equal to 1. So my partition function will be, function for one particle z1 equal to 1 plus exponential power minus beta epsilon. And then for n particle, it will be 1 plus exponential power minus beta epsilon for n. That is for total.
Okay.
Yes.
Okay. Very good.
Yes.
Actually, I think what Anand was saying is the correct answer. But I wanted to also tell that to get this correct answer, you have worked so much. So first thing is that since if they are non-interact, I am trying to tell you that in the process of giving the correct answer, you also gave some answers which are not all that correct. Okay. For example, you made one statement that you want to write Hamiltonian. Why you want to write Hamiltonian for this system?
No, sir. No, sir. This is by mistake. Here, no need to write the Hamiltonian.
No need to write Hamiltonian.
Yes, yes, sir. Here, directly.
Second thing you said is that since they are not interacting, potential energy is zero. That is also not correct, because even if they
Yes.
are not interacting, if there is an external force in which these particles are there, still potential will be there.
Yes.
Okay? So that is also not correct. But
Yes,
that
sir.
is not required because we don't have to write a Hamiltonian. Why we don't
Yes.
have to write Hamiltonian here?
Since here energy state, each particle have energy state is given. So
Yes.
yes.
We require Hamiltonian to find what are the energies. But in this problem, energies are given.
Yes, sir.
We don't have to. We don't
Yes,
have
sir.
to worry about the Hamiltonian. Right?
Yes, sir. Yeah, yes, sir. So actually, in case of actually, I initially I was studying classically. I was finding this. So I forgot to see this. You have given two energy levels.
Right.
That's
Okay. Fine. So whatever you said towards the end, that is the major advantage of particles being non-interacting. So the only advantage of particle being non-interacting is that you can write this total partition function for the n particles as partition function for one particle raised to the power n. This is the only advantage of non-interacting particles. Okay, and this is always true.
yes, sir.
Okay, where z1 is partition function of single particle. If they are interacting, this cannot be written. So this
Yes.
is one trick that you always should remember. This cannot be written if particles are interacting. Okay, so in solving problems, keep this in mind that you can write like this if the particles are non-interacting. Now, we have to find out Z1. Okay, now if you take one particle, like in this case, what are the allowed energies? 0 is one energy, epsilon is one energy. So what is partition function? The Boltzmann factors corresponding to every energy. That's all. So you have e to the power minus beta into energy 0 plus e to the power minus beta into energy. So what is this? This is simply 1 plus e to the minus beta. Correct? So you can write down the partition function as 1 plus e to the minus beta epsilon raised to the power n. Okay, is this clear? Any doubt? So far it is clear.
Yes, sir.
Okay, so now we have obtained the partition function. Okay, now let's say that we are interested in so our partition function is z is equal to 1 plus e to the minus beta epsilon raised to the power n. Okay, so for example, I want to find the entropy of the system. Find entropy. Okay, so let me now, let's say Srivardhini, are you there?
Yes, sir.
Srivardhini, how do you find entropy?
I don't know, sir.
Okay, what thermodynamic quantity you can find? This is an easy question.
Temperature.
Partition function is given, but which thermodynamic quantity can you find? Can you find internal energy? Internal energy of the system? Jahan Pratap? Jahan,
Yes, sir.
so can you find entropy?
Yes,
How do you find it?
it's given by the
Can you write?
Boltzmann KB logs it. Okay, sir.
Can you write or?
Let me try to write, sir.
Okay.
Sir,
So you are going to use this formula,
to find entropy, yes.
but is this formula correct?
I guess, yes.
Anyone has any objection to this formula or correct?
Yes, sir. It's actually, it should be find out F is equal to K minus KB TLNZ, Helmholtz free energy, and it is incorrect. He have written in the microcanonical ensemble S is equal to KB ln omega. That is microstate. Say here instead of writing Z, it should be omega. And also here it will not be useful. Here Helmholtz free energy we have to find out first.
Yes. So you cannot use this formula because there is no such formula. The this is not correct because the this particular canonical partition function is not related to entropy like this. This formula is fine, as Anand was saying, that if you take kb logarithm of omega in microcanonical ensemble, you find out this number of microstates, then entropy is related. This is our Boltzmann formula. So here you don't have this one, but you have Z. So Z is not related to that. Correct? So what you have to do is you have to first write down Helmholtz free energy. Helmholtz free energy is equal to minus kBt logarithm of Z. Minus kBt logarithm of Z. And you know F is equal to U minus Ts. Correct? So that means you can write down dF as du minus TdS minus SDT, but du is TdS minus TdV minus TdS minus SDT. So your TdS will cancel and you have entropy as minus partial derivative of F with respect to. Okay, so you want to find out S, then you have to first find out F and then obtain S as a negative partial derivative of F with respect to. So if you have a canonical ensemble, if you have a canonical partition function, finding out S is a two-step process. First you find out F and then you find out S. Okay, so this is, and so I asked a question that how do you find out U? How do you find out U?
Minus del by del beta ln z.
Yes. So U is equal to, you have a direct relation that minus partial derivative with respect to beta of logarithm of z. Okay. So that is going to give you minus k beta n logarithm of 1 plus, sorry, this is not correct. So you have F is equal to minus k beta t into n into logarithm of 1 plus e to the minus beta. Okay, or I can write this beta epsilon as epsilon by kt. Why I should write it as epsilon by kt? Because I'm going to look at e to the minus epsilon by k. So what is entropy? Is minus ρf dot. So minus minus will be plus, but there is a t sitting here and there is also t sitting here. So we have to use a product formula. So kbn logarithm of 1 plus e to the minus epsilon by kt plus n kbt divided by 1 minus e to the minus 1 plus e to the minus epsilon by kbt into e to the minus epsilon by kbt into epsilon by kbt square. Correct? There is a minus sign coming from here, then 1 by t is minus 1 by t square. So that will cancel away and you have something. Okay. So this is the expression for the entropy. Now suppose if I asked question that what is this entropy as temperature becomes infinity? What is this entropy as temperature becomes infinity? Arya? Arya Kauri?
Yes, sir. As temperature increases to infinity, entropy should be going to, it should be high also.
So can you evaluate? You have now the mathematical expression on the board. Can you evaluate?
So if we take the limit to, like integrating that to,
So it's not very difficult to evaluate that limit because wherever 1 by t is there,
yeah, there
that
we
term
can
will
put 0.
0. So the second term will go to 0. That is, this term will go to 0 because there is a t here and by t square there. So there will be 1 by t overall. So that term will go to 0.
And e
Correct?
raised to 0. Yes, sir.
And here what happens to this term as
Uh,
temperature becomes infinity? This
e raised to
becomes
0.
0, e raised to 0. So that is 1. So it will go to
KB, L,
n kb
NKB,
log.
not 2.
Okay.
Yes,
Now
sir.
this is understandable because each of the particle has got two levels. Okay. And at infinite temperature, what happens? Both of them become equally probable. Correct?
Yeah,
Because the probability of this one is same as this
similar.
one at infinite temperature. So it is like I have two possibilities like head and tail, which are equally probable. This is the entropy. Correct?
Yes, sir.
So nkb logarithm of 2 is the probability of this one. So this we could have guessed it. So sometimes we should develop this habit of guessing what happens in different limits of this temperature. So that is what we can. What happens in the limit t tending to 0?
If t tends to 0, this second term will be infinity because there will be 1 by t there.
Hmm.
And in the first term again, e raised to 0 will, e raised to infinity will be coming.
Hmm.
So
But what do you physically expect?
physically entropy should be minimum, like when temperature is very low.
So as temperature goes to 0, as temperature goes to 0, what do you expect?
It should be a very low low entropy.
So
So
you expect it to be 0?
we can like it theoretically maybe we can say it's 0, but I don't think it would be 0.
No, see, physically you have first particle, second particle like this, right? So at 0 temperature, no particle will have enough energy go to the excited state.
Yeah,
Correct?
yeah,
So that means what happens? All particles will be in the ground state only.
yeah,
So how many microstates will be there of that type? There's only one microstate. It is like all our heads
yeah,
or all our tails.
yeah.
So there is the number of microstates of such a configuration is only one, right?
Yes, sir.
So the entropy will be k log 1, so that is 0. So you should get 0 as t goes to infinity, t goes to 0.
Yes,
Correct?
sir. Yeah.
So are we getting 0?
Here, loan of um,
So this one, 1 by t goes to 0, 1 by t goes to infinity. So e power minus infinity is 0.
Yes, sir. So
Correct?
ln
This
1
becomes
again
simply
goes to,
logarithm of 1. Logarithm of 1 is 0.
yeah.
Okay. Now
Yes.
this term, so if you look at this term, how that term looks like is,
T will be 0
so
then.
let us write n kb into epsilon. So kb anyway will cancel because this kb is there and this kb is there. So n epsilon by t, correct?
Yes,
And
sir.
suppose if I take this factor to the denominator, then I will have 1 by e to the power epsilon by kt
Maybe.
kbt plus 1, correct?
Um,
This is the second term. I am writing this term here,
mm.
correct?
So this e raised to minus epsilon by kbt, we brought it down. And
Got it
this,
down. Then
yeah,
it will
this goes,
become plus,
okay.
right?
Mm.
So that is what I have written.
Yeah.
Now, suppose if t becomes very large, okay. So sorry, t goes to
And
0.
t goes to 0.
As t goes to 0, then e power epsilon by kt kbt. This will be a very large number compared to 1.
Yeah.
So
So we
this
can
can be
write,
written as simply e to the power epsilon by kbt.
yeah.
Correct.
Yes, sir.
Then it can be taken to the numerator. So you have n epsilon by t into e to the power minus
kbt.
epsilon by kb. So this is the, as t goes to 0, this denominator also goes to 0 and the numerator also goes to 0. Correct.
Yes, sir.
But the numerator exponentially goes to 0. So the numerator is a dominant function.
Mm.
Correct.
Yeah.
This exponentially goes to 0, whereas this goes to 0 only as t. So this overall will go to 0 because e to the minus epsilon by kbt goes to 0, faster than t goes to
Okay,
0.
right. Yeah.
So overall this term also will go to 0, and hence this limiting case is correct.
Okay.
Okay.
Yes, sir.
Now we can ask, so we have this z is equal to 1 plus e to the minus beta epsilon raise it to the power n. So this is our result of our statistical mechanics. So we are already starting with this. Now we know that this internal energy is given by dou beta of logarithm of z. So that is equal to minus dou beta of so there is a n which I can write like this outside logarithm of 1 plus e to the minus beta epsilon, which is equal to minus n divided by 1 plus e to the minus beta epsilon into e to the minus beta epsilon into minus epsilon. So your average energy is given by n epsilon divided by e to the power beta epsilon plus 1. Is that correct? Yeah. So your internal energy is given by n epsilon divided by e to the power beta epsilon plus 1. Okay. So now somebody tell me, okay, Ashwati, are you there? Ashwati?
Yes, sir.
Ashwati, can you tell me how will you find out CV?
Mm, and CV is dou u by dou t.
Very good. So CV is dou u by dou t. So which we have already an expression for u. So you can find out dou u by dou t. Can you write, Ashwati?
Sir, I don't try.
Are you using mouse? Ashwati, are you using mouse?
Yes, sir. It's difficult to write. Shall I say it?
Okay, okay. No problem. I just wanted to know whether you are using mouse or
Yeah, it's not mouse, sir.
it's not mouse.
It's not mouse.
Okay. Are you on the mobile?
No, sir, laptop only, but with the
For that
uh,
whatever joystick
uh,
like thing.
uh, the beta is 1 by kbt. So
Okay. So you have to write that one. That is, you have to write dou by dou t of n epsilon divided by e to the power
1 by
epsilon
k.
by kBt plus 1. So this is something which we can write minus n epsilon divided by e to the power epsilon by kt plus 1 whole square. This minus sign is coming because of this differentiation, and differentiation of this one, that is e to the epsilon by kbt into minus epsilon by kb c square. Correct? So you can write this minus sign here and this minus sign here will become plus. So you have n kb into epsilon by kbt the whole square, okay, epsilon by kbt whole square into 1 by e to the power epsilon by kbt to the power epsilon by kbt plus 1 whole square. So as you can see that this is what we called as Schottky anomaly. Schottky anomaly in spin systems when we studied. Schottky anomaly. So I have shown you at that time, if you are plotting temperature dependence of this specific heat, it will show a peak like this, and in the both sides, as temperature goes to 0 and as temperature goes to infinity, it will have a decaying behavior. And that is not very difficult to see, because if what happens as CV goes to, so we have CV as nkb into, let us define this epsilon by kbt as some value, some variable x. So you have nkb, or I can also write down this as CV by nkb. Okay, that is equal to x square divided by e to the x plus 1 whole square. So this is the kind of function. Now this function has a maximum. Now what happens if t goes to infinity? If t goes to infinity, that means what? X goes to 0, correct? Because x is given by epsilon by kb. Similarly, if t goes to 0, that that translates into x going to infinity. Is that correct? So t going to infinity means x going to 0. T going to 0 means x goes to infinity. Now we can ask a question: what happens to this CV by nkb as t goes to infinity? That means x going to 0. So x is going to 0. This becomes what? This is 1. This is 1. So you have 1 by 4. So this goes like x square. So this goes like x square. But what is x? X is epsilon by kbt whole square. So this actually goes like 1 by t as t goes to infinity. Now what happens to CV by nkb as t goes to 0, which is the same as x going to infinity. Now if x goes to infinity, you can see that e to the x plus 1 can be written as simply e to the x as x goes to infinity. And because of that, this becomes x square into e to the minus x. So like in the previous case, e to the minus x, e to the minus x as x goes to 0, x goes to infinity will go to 0 faster than x square going to infinity. Okay, so that is e to the minus x goes to 0 faster than x square going to infinity as x tends to infinity, and hence the overall function will decrease like e to the minus x. So if you are remembering our expression, that is if you plot CV by nkb here and then x here, then you have a thing, and in this particular region it will go like e to the minus x, and here it will go like x square. So if you are writing like in this case, if you are writing this t, in this case this will go like 1 by t square, and here it will go like e to the minus 1 by t. So that is the behavior of this specific heat, namely the Schottky anomaly. Now we can ask a question: what is the probability of, okay, so let's not ask that question. So let's say we ask this question: suppose we have n particles, right? N particles. Okay, so we can ask at some temperature T, how many particles are in the excited state. Of course, it is a statistical question, so we have to add this caveat saying on an average how many particles are there in the excited state. Okay, so Ashlyn, are you there? Ashlyn?
Sir, sir.
So can you answer this question? At temperature T, how many particles are in the excited state on an average?
We have to find the probability density
Hmm.
by using the partition function like how many particles are present in excited state at T by total partition function.
Correct. So can you write?
Sir, I cannot write it.
You cannot write it.
No,
Okay.
I
So
tried it, sir, but it's difficult for me.
no problem. No problem. So can anybody else write what she wanted to say? Okay. So can someone write? You can choose. I mean, you can volunteer to write because I am not clear who is there. Abhijit, can you write?
Sir, it's difficult to play. I have
Difficult to
only
write?
touchpad here.
Okay. Okay. So you have to first find out. So what Ashley is saying is that you have n number of particles, and then multiply this with probability of the occupation of the excited state. Okay, this is the number of particles occupied as n1. So let us define n0 as number of particles in the ground state, and n1 as the number of particles in the excited state. In the excited state. Okay, so n1 is equal to n times, of course, needless to say that n0 plus n1 should be the total number. Okay. So n1 should be written as n into p of n. So what is p of n?
So it's a distribution function.
So what is that equal to?
Exponential power minus beta epsilon divided by z.
So p of epsilon is equal to e to the power minus beta epsilon divided by
Z.
z. Is this z or z1?
Z. This is Z1 for one
Z1.
particle. Yeah.
One particle. Okay. So your p of e is given by e to the power minus beta epsilon divided by 1 plus e to the minus beta epsilon, because that is our z1. What is probability of the ground state occupied? We call it as, let's say, p0. That is simply 1 by 1 plus e to the minus beta epsilon. So that when you write p of 0 plus p of epsilon, you get 1. Correct? That should be true. Okay. Now that we have p of epsilon, that is the probability of the excited state, as e to the minus beta epsilon divided by 1 plus e to the minus beta epsilon. Okay. Now let me ask you a question. What happens to this p of epsilon? What happens to this p of epsilon as t goes to infinity? what happens to T of epsilon as T goes to infinity?
So it will go to 1.
Which one will go to 1?
P of epsilon.
This one goes to 1.
Yes, sir.
Why? Because as T goes to infinity, what should beta go to?
Beta goes to 0.
It is half. It should be half.
So it is half. No? This the numerator become 1. This also becomes 1. So this goes like it is half. Okay. So what will be n1? N1 is equal to n into P of epsilon. Correct. So your n1 as T goes to infinity will be simply n by 2. Okay. Now, if you ask what happens to this probability as T goes to 0, as T goes to 0, what happens? T goes to 0 is actually beta going to infinity, correct? So, what happens in that case?
It is n1 exponential power minus beta e1.
Yeah. So like in the previous case, let's say you bring it to the denominator and then it will be simply e to the minus beta e, and e to the minus beta epsilon as beta goes to infinity will go to 0. So the probability of epsilon as t goes to infinity, t goes to 0 will go to 0. That means this number of excited state particles as t goes to 0 will go to 0. That means what? There are no particles in the excited state. All the particles are in the ground state. That is understandable because now if you imagine that this is your ground state and this is your excited state. Now suppose if there are some particles, suppose let's say all at time t equal to 0, let's say all the particles are in the ground state, that is your temperature T is equal to 0. Now as you increase the temperature, some particles will get some energy and they will try to go to the excited state. Now you go on increasing the temperature, more and more particles can go to excited state. Now what happens, even if you are increasing the temperature to infinity, that is as T going to infinity, what is the scenario? You have n by 2 particles in the ground state and n by 2 particles in the excited state. Okay. Now you can see that at the best, if you are going on increasing your temperature, maximum number of particles that you can on an average get in the excited state is n by 2, even at infinite temperature. It can never be more than n by 2. Is that clear? That is what is the result that we are getting by just analyzing this probability of the excited state.
Excuse me, sir.
Yeah.
So while finding the probability of excited state in the denominator, why we are taking Z1 only instead? Why not Z?
Okay. So when we are writing this, so when I am writing this n is equal to n1 is equal to n into probability of E. Okay, if I am writing like this, then this probability of E is the probability that a particle is in the excited state. Okay, so what does that mean? That means this A particle is what is important. Okay, so A particle I am talking about. So I'll have to write down P of epsilon as the Boltzmann factor corresponding to the energy for which I am interested in the probability plus a partition function of that particle alone. Correct?
Okay, sir. Okay.
So that since I am already multiplying this n here, I only ask what is the probability of a particle in the excited state.
So if that n is not there, we can use z itself, right? So,
You can actually talk about total Z. Okay, you can also talk about total Z, but then you have to also find out uh, the energies of the total Z. What I'm trying to say is total system. Suppose let's say that I have, for argument's sake, let's say I have 3 particles. Okay, each of this can be in 0 or epsilon. Okay, now suppose I have first particle, second particle, third particle. So all of them are in the ground state. Okay, then the energy corresponding to that one is 0 plus 0 plus 0 is equal to 0. Suppose you have a situation that first particle is in 0, second particle is in excited state, third particle is 0, then we have epsilon. Or you have a situation where 2 particles, first particle, second particle, then I have 2 epsilon. Now this situation can happen in 3 different ways, because I can have 0 epsilon 0 or epsilon 0 0 or 0 0 epsilon. So I have 3 states, right? 3 states, and this can happen in 6 ways. This can happen in 3 ways. Okay, so like that, suppose if I am interested in asking now, if I want to know all of them are in the excited state, then I have an energy as 3 times epsilon. Now if I want to calculate the total partition function, I have to write 1 plus 3 times e to the minus beta epsilon plus 3 times e to the minus beta 2 epsilon plus e to the minus beta 3 epsilon. Like this I have to write. And now if I want to calculate how many particles are there in the probability of the particles in the all of them are in the excited state, that corresponds to this energy, and that energy is e to the minus beta 3 epsilon divided by this Z. Okay, so if I do like this, I will get an answer directly. What is the all the that is my n1. I will get the answer directly. So whatever I have written here is an indirect way of getting, without doing all that calculation of the microstate energies of the total system. I simply look at the single particle and then get an answer for the average number. Okay, so this is a simplified version.
okay, sir. Thank you.
Sir,
Yeah,
sir, here N1 is the average number of particle, right, in the excited state.
correct.
So if it is average, we can also think of it like a expectation, like the first particle into the probability of the first particle being in uh, the probability of first particle being in the excited state plus a second particle into probability of, like that we will add up to n. So
Correct.
ultimately for each particle probability is same.
Correct.
So that will be n into probability of epsilon.
Correct. 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 Okay, so this is fine. Now I want to ask you this question, that when we did the spin system, we had talked about something called negative temperature. Okay, so now this negative temperature comes in the situation where N1 is greater than Nc. You can define something called negative temperature when N1 is greater than N0. Now, how we can get N1 greater than N0? Or if you are able to get N1 greater than N0, that is what we call as population inversion. And that corresponds to a situation of negative temperature, because we have seen that as that is, as t tends to infinity, n1 goes to n by 2. That's all. It can only half of them. And if you want n1 greater than n by 2, this implies that your n1 has to be greater than n by 2. Okay, but it is not. It does not happen even as t tends to infinity. But if it happens, then okay. So if it happens, then we must realize that the temperature T for such system should be what we call as hotter than the hottest. Why I am saying this hotter than hottest? Because hottest is infinity, and if this happens, that means you are able to promote more particles than n by 2 to the excited state. That means it is even hotter than the hottest. Okay, so that is what we define as the negative temperature, and then you can see that the negative temperature system will be hotter than any of the positive temperature system. Okay. So now the question is that is it possible to, so can we get n1 greater than n by 2? This question is equivalent to asking, can we get probability of epsilon greater than 1 by 2?
Sir, usually in if we do not stimulate the system just by means of temperature, but by other means, then it is possible. Propulsion inversion is possible.
Okay. So suppose if I ask this question that, so we can see that in our present situation, your P of epsilon goes to 1 by 2 as T goes to infinity. This is what we have observed, correct? So can I do something, or can I use some system, of course two-level system, such that P of epsilon goes to some value. Okay, so let's say some value r, let's say, as t goes to infinity, where this r is greater than r. Okay, so this seems to be an interesting question and a good question to ask. Is there something that I can do to the system such that I can achieve this? That is with the system that I have worked out so far, I will not be able to get this thing done. But can I do something? Can I change the system a little bit and then achieve this? Okay, so it turns out that, are there any suggestions?
Sir,
Do you have any suggestions? Are there any suggestions to achieve this?
here we did not consider a spin system.
I want it to be a two-level system, but then you can make some modifications to two levels.
So we can include
No.
degeneracy.
Yes. So I think we should include degeneracy. So that is a good suggestion. So let us play with that. Okay. So degeneracy is the key concept. Suppose I have a system where the ground state is non-degenerate, but excited state is doubly degenerate. Okay, that means there are two energy levels corresponding to excited state, but there is only one energy level. This has an energy 0, this has an energy epsilon, but there are two levels corresponding to excited state. Now in this case, what happens to your P of epsilon? Your P of epsilon is something like, how do you write this P of epsilon? Abhijit, P of epsilon.
I don't know, sir.
Suppose, how do you write Z1 for this?
Z1 is like e to the power minus beta into that energy.
That first one is 1 because energy is 0.
Yes.
Plus
second one, we can do that whatever the number of degenerate state.
So that is 2 into e to the minus beta epsilon. Correct?
Yes.
So now what will be P of epsilon?
E to the power minus beta e by Z1.
E to the minus beta e by Z1. 1 plus 2 into e to the minus beta e. But that is not correct, because we are interested in probability of the excited state, but there are two excited states. But we don't care whether it is in this excited state. So you have to put a 2 here. Correct? We are interested in only probability of that energy. Correct? Now what happens to this one, P of epsilon, as t tends to infinity?
That t tends to infinity, beta tends to 0, so it will be 2 by 3.
It will be 2 by 3. So we have achieved that, because 2 by 3 is greater than 1 by 3. Okay. 2 by 3 is greater than 1 by 3. So one way of getting more particles in the excited state is to make the excited state degenerate. So by increasing the degeneracy of the excited state, we will be able to get more particles in the excited state. This is not negative temperature, by the way. This is still a positive temperature. Even at positive temperature, you have so your average, your N1 is going to be equal to N2N by 3 in this case. Okay, average number of particles in the excited state is equal to 2N by 3. Okay, so this is kind of discussion that so you can see that we have learned quite a bit of statistical mechanics by just using the simplest system called the two-level system. Okay, so I started with asking the question, we have n non-interacting particles. First, how to write down if they are non-interacting, then we can use this scheme that you find out the partition function for the single particle, and then the partition function for the entire system can be obtained by raising this to the power n. Partition function from the single particle is simply 1 plus e to the minus beta e. Then the total partition function is given by this. Then we asked a question, how do you find S? And to find any thermodynamic quantity, the first thing you have to do is get the Helmholtz free energy. And from the Helmholtz free energy, you can get entropy by taking negative partial derivative of the Helmholtz free energy with respect to temperature. Then we have found out entropy by taking this, and then we asked what is entropy as temperature tends to infinity. That is simply nkb logarithm of 2, because both the energy levels are equally probable in that case. There are two possible states. It is exactly like coin toss, head or tail. And then as s goes to as temperature goes to 0, all the particles will be in the ground state. There is only one microstate, and hence the entropy has to go to 0. So we argued that this expression that we derived here will agree with what we expect in these two limits. Then we try to find out the internal energy using our formula like this. Now let me also tell you that you could have found out internal energy in this fashion. Also, you could find out internal energy, because now you have F and you have found out S. Then you can simply take U is equal to F plus Ts. Because F is known, S is known, F is known, and S is known. You can find out U as F plus Ts. Okay, so this is one way, and you could have also found out U as F plus Ts. This is another way. Okay, so we found out U, and then we found out CV, and CV is simply partial derivative of U with respect to T, and then we figured out that the Schottky anomaly could be reproduced, and we have this. Then we looked at what happens to temperature tending to infinity and temperature tending to 0 behavior of this specific heat or the two-level system. It goes like e to the minus x and x square. And if you translate this into the temperature behavior, high temperature region will go like 1 by t square, and low temperature region will go like e to the power minus 1 by t. And this is the Schottky peak that we have. Now, then we ask the question that how to find out how many particles on an average are there in the excited state. So you can get that answer by taking total number of particles multiplied by the probability of the particle in the excited state, which is obtained by this Boltzmann factor e to the minus beta epsilon divided by Z1. And so we got that expression also evaluated in the limits, t tending to infinity, beta tending to 0. This is half, and maximum number of particles at infinite temperature is only n by 2. So we then asked the question that is it possible the negative temperature that we have discussed earlier corresponds to a situation where n1 is more than n0. That means n1 should be more than half the particles. If this kind of a scenario happens, then we must realize that temperature for such system should be hotter than the hottest. Then we asked the question, even at positive temperature, how is it possible to make this probability greater than 1 by 2? Then that can be done by increasing the degeneracy of the system. So this is something which is not a negative temperature, as you can see. Even at positive temperatures, you can actually make this 2 by 3 greater than 1. Now, one can ask a question that, yeah.
So how can we introduce degeneracy to a physical system?
We can introduce degeneracy of physical system um, by increasing the symmetry. Okay. For
Right, I didn't
example,
get you there. Increasing.
okay. So let me give you one example. Suppose, let's say that I have let's say I have so let me just consider uh, a particle in a rectangular box like this. Let's say this is 0 to L1 and this is 0 to L2. Okay, so imagine that I have a particle in uh, in a rectangular box. Okay, so rectangular box. Now the energy levels of these particles will depend upon, of course, two quantum numbers n1 and n2, which is given by h bar square. I am just borrowing the idea from uh, the particle in a box solution. Twice m into we have n1 square by L1 square plus N2 square by L2 square. Okay, fine. Now the ground state of this one is corresponding to E1 comma E1, E1 comma 1, correct? So that is equal to h bar square pi square by twice m into 1 by L1 square plus 1 by L2 square. So this is the ground state energy. Then you can have your excited state. So let's assume that L1 is greater than L2. Without any loss of generality, assume that L1 is greater than L2. So your since L1 is a larger value, so N1 square, so E2 comma 1 is equal to h bar square pi square by twice m into 4 divided by L1 square plus 1 divided by L2 square. This is the first excited state of the system, correct? Then you have 1 comma 2, which is equal to h bar square pi square by 2m into 1 by L1 square plus 4 by L2 square. Okay, 1 by L1 square and 4 by L2 square. So that means, and let's assume that there are infinitely many levels. Okay, so let us ignore these levels for the time being. Now we have these energy levels like this. This is E1 comma 1. Then I have E2 comma 1. Then I have E1 comma 2. Okay, so these are the energy levels, and of course there are also many energy levels above this. Okay, for the time being, let's assume that we don't consider them, or the higher energy levels are so high that our system is not going to get excited to those levels anytime. Okay, so now what happens? Suppose if we do something to the system, or we choose another system where we have a symmetry, in the sense I don't have rectangular box, but let's say I have a square box. That means L1 is equal to L2. This is symmetric, because what is the symmetry? Your suppose if you call this as x and this as y, x going to y, there is no change in the system. System's Hamiltonian. So if L1 is equal to L2, then what happens for this particular case? You have ground state, that is E1 comma 1, and you have two degenerate excited states, that is E1 comma 2 and E2 comma 1. The energy is same, but the states will be different. So you can see that this 3 non-degenerate states can now be considered as, it can be obtained as 1 ground state and 2 uh, 1 excited state with double degeneracy. So in general, you can introduce degeneracy into the system by increasing the symmetry of the system. Now, how to increase the symmetry of the system is a physical problem. One can do it uh, by by some application of external fields or choosing a different system which has this inherent symmetry and so on. Suppose I choose a material which does not have the symmetry, maybe I choose another material which has this symmetry. So that way I can alter the energy levels of the system. Okay. Is that clear?
Yes, sir. Yes, sir. Thank you, sir. Sir, I have another question.
Yeah.
Sir, while solving this problem, we considered it as a canonical system, right?
Correct.
Yeah. Why did we prefer that over macrocanonical ensemble?
In this problem, actually, there is no difficulty in doing it in microcanonical also. But like for example, if you are choosing microcanonical, how you would have done it? You will say that there are total n number of particles, and among them, let's say that there is n0 of them are in the ground state, and you ask a question in how many number of ways this can be chosen. This n0 can be chosen. That can be chosen in n factorial, n0 factorial into n minus n0 factorial. Okay, so this is how you can choose, and now you can relate this n0 to your energy, because n0 into okay, so your energy, total energy is given by n minus n0 into epsilon. Okay, this is this one. So your n0 n0 into epsilon is equal to n epsilon minus e, or you can write down your n0 as n minus, or you can write down n minus 1 minus e by n epsilon. Okay, so if you remember, we have called this e by n epsilon as some u in our two-level system calculation. So, so n0 is n into 1 minus e. Okay, so this is our n0, and you can find out, you can substitute, so you can write s is equal to kb logarithm of omega, and then substitute this value for your n0, and then obtain u and other thermodynamic quantities from here. So this is how we do it in microcanonical ensemble. So this particular system is very easy to solve in either of these ensembles. Okay, so there is no difficulty, but there are many systems which are very easy to solve in canonical ensemble.
Okay, sir. Thank you, sir.
Any other questions?
Excuse me, sir.
Yeah.
Sir, yeah. Sir, you took here you took for total partition function. You said that z1 to the power n will be the total partition function. If there are n non-interacting particles. Could you prove this statement for any non-interacting system? I mean, not obvious for me.
Okay, proving that one is something like this. So if you have, so let's say you have Hamiltonian for if you have n number of particles, the Hamiltonian can be written as Hamiltonian for each of the particle I is equal to 1 to n into hi. Okay, we can write like this.
Yes, sir.
Okay. So now let's say that we have the partition function. I'm just using one of the classical expressions that we were familiar as dq bar and dp bar. into e to the minus beta h, and
Yes,
if
sir.
we can write this,
Sir, sorry for interrupting. I mean, this way I can understand that since there are independent variables, you take its power n. When we
yes.
have summation, when we have summations, I mean, when the labels are discrete, that is what I want to know.
Yeah. So what actually happens in that case is, suppose if you have z is equal to sum over I e to the minus beta ei. Now this ei is energy of the ith microstate of n particle system. That's what you have to
Yes, sir. Yeah.
correct, n particle system.
Yes, sir.
So now this microstate n particle systems energy you have to first find out, and that is what I tried to show here, taking this example of three particles.
Yes, sir.
Suppose if I
Free.
have three particles, I have this 0, epsilon, 2 epsilon, 3 epsilon, like that, correct? So I can have
Yes,
energy
sir.
3 epsilon, but there is also degeneracy, right?
Yes,
This
yes,
will
sir.
have
Yeah.
3, this will have 3, and this will have 1. So then the partition function is written like this. But you can see that this is exactly
The
as 1
cube of.
plus minus
Yes, sir.
beta
Yeah.
epsilon whole cube,
Yes, sir.
right? So these if they are non-interacting, these degeneracy indices are exactly these binomial coefficients.
I mean, will this go for systems with more than, I mean, having more than two energy levels?
Yeah, then also there is no problem, because suppose if you have, let's say I have 0, then epsilon 1 and epsilon 2, like that. Let's say there are n energy levels. Okay. Suppose there are n energy levels
Yes,
for
sir.
each particle. Hmm. Uh, that is, each particle 1 has 1, 2, etc. There are n energy levels. Similarly, particle 2 has 1, 2, etc. There are n energy levels. So in this case, my z1 becomes 1 plus e to the minus beta epsilon 1 plus e to the minus beta epsilon 2, etc. This will be e to the minus beta epsilon n. Correct?
Yes, sir. Yes, sir. Yes, sir.
So what will happen to the total partition function? It is same. If they are non-interacting, this is going to be 1 plus e to the minus beta epsilon 1 plus, etc., e to the minus beta epsilon n raise it to the power n. Correct?
Yes,
Now,
sir.
now what happens if you are actually trying to evaluate these degeneracies? Then you get so you get these coefficients as multinomial coefficients. That means
Yes.
if, let's say, there are n0 particles in 0 and n1 particles in epsilon, like that. Let's say there are n. Okay, maybe I should have written some other index. So let us take. Okay, let us take some omega 0 particles in 0 and omega 1 number of particles in epsilon, and such that omega n in epsilon n. Like this, if you have number of particles, that number of particles. Okay, then you are going to have your uh, energies can be obtained like this. But you know that this omega 0 plus omega 1 plus omega n, that should be equal to total number of particles, correct?
Yes,
Total.
sir. Yes, sir.
Then the coefficients of this one will become n0 divided by n0 factorial divided by omega 0 factorial, etc. Omega n minus 1 factorial, and the last one will be capital N minus omega 1, etc. omega n minus 1 factorial. So this is multinomial coefficient. So these coefficients will become degeneracies in this expansion. So the binomial thing will simply become multinomial coefficients here, but this will still work as long as they are non-interacting particles. If they are interacting, then those interaction terms will be there. So we cannot write H as H sum over I HI.
Sir, if the particles are identical, we have to divide by n factorial. Is it correct?
Yeah. So if you have indistinguishable particles, then you have to write Z as Z1 to the power n divided by factorial n, like in the case of ideal gas, for example.
Okay, sir.
Any other question? So maybe you can tell me how is this approach. Of course, maybe we will not do it every day, but I mean, if you like it, we can also do it. Is this better, or my doing a continuous lecture is better?
Sir, I think this is better.
This is better. Okay, one vote for this.
Yes, sir, this is better.
Uh, two votes.
Yes,
Sir,
this
this
is
is
better. Four.
This is better. Okay, is there someone who says this that is better? Because there are 50 people and only getting 5 answers is too underrated response. Of course, I have to check whether I can. Can I make a PDF of this file? I don't know. Download as PDF. Open it and do it. Great. So then I think that's fine. You can also download this as PDF. So then we should probably continue 1 or 2 classes like this. And so today's whole class, try to I only try to look at what is called the 2-level system, and wanted to discuss. And if you look at some of the questions that you would have you will see in these competitive exams, they will be more or less on these 2-level systems. Okay, so they may ask you this limit, that limit. So if you understand 2-level system thoroughly, you can say that you have understood most of statistical mechanics, because the applications of 2-level systems are also quite many. So there are many problems in which these techniques of 2-level systems become handy. So a good understanding of 2-level system is almost learning statistical mechanics. So I thought Benexi will say something. Benexi, is this method better?
Sir,
I think you had some network problem. You went out and came.
yes, sir.
So when you are not there, I asked a question. is this interactive thing better, or my giving lecture in OneNote is better? That's what I asked.
Sir, interactions. I have replied in the chat box.
Oh, you replied in phone. Sorry,
Yes, sir.
I haven't read the chat box. Maybe some people have replied.
This one is better, sir. Interactive section is better.
Okay. So probably.
So from an aesthetic standpoint, one note lecture is better. Only from an aesthetic standpoint. From an experience perspective, this is better. I mean, if you had to consider every aspect of it.
But anyway, I think aesthetic is not important. Aesthetics are more important only for giving a seminar or giving a popular lecture or something like that. But for teaching, I think learning is more important. And if you are learning better in this method, I think we should follow this method.
So, sir, within a gap of 2 to 3 classes, you can have some problem-solving sessions also like this.
Okay. Okay. But only I little bit. I was feeling that many of you are not able to write. But if you can write, that will be great. That is only difficulty that I found. But otherwise, I think it was fine. I don't have any difficulty of writing either here or there. Both are fine for me. But if you also can write, then see, like what is difference between this class and other classes? Can somebody point out clearly?
So here it is like almost all of them think what is happening.
And also same time, now we are at home and no one is nearby sitting as. So when you say something, we will feel like we are in classroom.
Okay. So when I call, you don't know who will be called next, so you have that involvement. Otherwise, you are feeling that you are at home, right?
Exactly, sir.
Okay. No, that's okay. I think I understand the spirit of your statement. But what I'm trying to say is that when I'm asking a question, and then you are able to answer or you are not able to answer, in any case, you are able to understand what is the difficulty, right? So that is what is very important. And how to write down a partition function for a two-level system with just two energies. There may be some of you who did not think about this earlier. There may be some of you who were not able to write earlier. But if you don't do this kind of class, then we may complete the entire course, but still you will not be able to write partition function. So that is what is. So attending any number of lectures will not be enough than having a hands-on experience. Okay, so this is what I wanted to demonstrate by doing this, attempting this one today. So we will continue for some more time, 1 or 2 more classes like this, and then see how much progress we make. Because now that we are almost ending our canonical ensemble lectures, it is important that you should get a hang of how to use these techniques in solving various problems. Only then we can say that, okay, we have learned this. Otherwise, just knowing some formal definitions and aspects is not of much use. We should know how to use them in various applications. Any other comment anybody has?
So before this class, earlier whatever theory and whatever formulas we have learned, we didn't know how to apply.
Yeah.
Now with the example, now I get to know what should we do with the problem, how to approach.
So that is what is the business actually. The business is always see, it is like if I read a book on how to swim, I don't think I can go and jump in waters and swim, right? So knowing all the theory that I am teaching is like reading a book on swimming. but that is not going to help you swimming when you are in waters. So actual swimming has to be learned in swimming pool or in a well or in a sea, whichever. We have to jump in waters. So the exercise that we have done today is actually learning swimming. Okay, that is a big difference between reading a book on swimming and swimming. So most of the times, if we don't do this kind of exercise, it is like we read a book on swimming and learn how to swim theoretically, and when we actually find ourselves in water, we get drowned. Okay, okay, then we will close for today, and again in the next class we will continue the same jam board. In the meantime, you also think and try to see how best you can participate. If you want to practice a little bit of writing in the back jam board, you can practice so that we can have more interaction. And
Sir, one small doubt, sir.
yeah,
Sir, it was said that certain systems can be solved by using either canonical or micro-canonical ensemble.
mm-hmm.
No, sir.
Mm-hmm.
But in micro-canonical ensemble, we have equiprobable microstates. But in canonical, we don't have that equiprobable microstates, no, sir.
Correct.
So systems can be solved by using either canonical or microcanonical, but in microcanonical we have equiprobable, and in canonical we don't have that. How do I reconcile both
See,
the ideas?
the point is choosing an answer. So please understand this one. Choosing an ensemble is like choosing a coordinate system. You can work with any of the ensembles for any problem. But suppose you attempt to solve hydrogen atom problem, let's say quantum mechanics of hydrogen atom problem in Cartesian coordinates, it is almost a suicidal kind of a choice because that is so difficult. But if you choose spherical polar coordinates, it's so easy, relatively easy to solve. But if you choose Cartesian coordinates and you want to solve hydrogen atom problem, if you try it, then you will know how difficult it is. So, like that, there is a certain ease in solving some problems with respect to certain ensembles. Some problems can be easily solved in canonical ensembles, some problems can be easily solved in grand canonical ensemble, etc. But all these ensembles will give you same thermodynamic results. In the sense, in thermodynamic limit, all these ensembles are equivalent. So, now your question is about how to reconcile with postulate of equal a priori probabilities, that is true in microcanonical ensemble and not true in canonical ensemble. And that is what we discussed in the very beginning when we try to move to canonical ensemble from microcanonical ensemble. When you consider a system and its environment together as a isolated system, the microstates of the composite system are all equally probable. So this unequal probabilities of the system can be derived from the equal probabilities of the system and the surroundings. Okay, so when you are trying to evaluate the system in the thermodynamic limit, this difference will get masked, and you will have in that limiting case, you get the same result. So mathematically speaking, choosing any ensemble is almost like choosing a coordinate system. Okay, so you can get thermodynamic results by choosing any ensemble of your size, but some ensembles are more easier than the other ensemble. So as a scientist, we will be interested in getting the results quickly and doing calculations easily without mistakes, and hence we always should choose that ensemble which is simpler for a given problem.
Okay, sir. Okay.
Okay, so okay, I think Shubhankar Mishra asked about chemical potential term in DF. Shubhankar Mishra, it is there. I did not write because I was only more interested in getting the entropy. So it is also there. And since I am going to take a derivative at constant n, I did not write, and my writing did not affect it. Otherwise, it is